So before we get into ocean's role in climate change, we have one more concept to conquer, and that is the ocean's response to buoyancy forcing. What is buoyancy? It's basically cooling, warming, and changes in density near the surface. So I think some of you are already aware of the so-called thermohaline circulation, temperature and salinity, which means density driven circulation, which is not really independent of the wind driven circulation, as we will see, but nonetheless oftentimes for the purposes of pedagogy you can separate the ocean circulation into wind driven and thermohaline circulation, and we looked at some aspects of wind forcing and wind response and spread of transports and so on, including western boundary intensification, etc., which are primarily wind related. But we will see that winds will change if you say change the thermohaline circulation, and thermohaline circulation of course responds to wind changes as well on some time scales. So let's start with recapping some of the things we have seen before. We looked at the sea surface temperature distribution with the 27-degree isotherm marked with these dark or solid black lines, and the 5 millimeter per day rainfall marked with these dashed contours. So here we have rain and E minus precipitation showing the subtropical gyres where the Hadley cell comes down and the rain is pretty much zero. So you have the deserts of the ocean and rainfall in the ITCZ, SPCZ, the Special Indian Ocean region, and the mid-tropics, mid-latitude storm tracks as well, with some differences in the southern hemisphere because of the Southern Ocean being very unique. So this gives us the freshwater forcing, and we looked at the salinity budget, and of course we also looked at the heat budget, and so we looked at the sensible heat and latent heat flux from the surface and said under the subtropical gyres where there is a lot of evaporation and trade winds, we get large latent heat losses. And of course in the ocean when you do that, and of course you also have large heat losses from the ocean where the subtropical the western boundary currents bring the warm tropical waters in under the cold atmosphere, and where there is upwelling the ocean takes up the heat. When evaporation happens, there is also salt left behind in the ocean. So salt is kind of the equivalent of humidity in the atmosphere. So what happens to the ocean when you have this kind of heating and cooling and changes in density? And we had looked at the meridional profiles of the heating and cooling as well. All these things come together to give us something that is very interesting that I'll first describe with a few figures of data to contrast, for example, the annual mean temperatures at the surface between, let's say, North America and Europe at the same latitude. And you can see that the ocean is warm, of course, in the tropical band, and there are deserts, and then you have the western boundary current bringing here the Gulf Stream, bringing warm currents all the way into the North Atlantic, into Norwegian Sea and so on. If you look at the same latitude, the temperatures here are tremendously cold compared to the temperatures here. 20, 30 in the winter can be even larger differences in how cold it gets with the continental air westerlies blowing here versus air coming off of the ocean onto Europe. And of course you'll notice also that the temperatures over the oceans are somewhat different, but when we look at the salinity, then you see that the salinities in the North Pacific and the North Atlantic are really different. You can look at these salinity maps and try to say which season they correspond to. So you have to be very careful, because if you look at the salinity here, for example, the ITCZ here is strong, rainfall is strong here, and the salinity is of course always higher than in the Arabian Sea than the Bay of Bengal, but here you can see that the contrast is much larger. So Arabian Sea is evaporating more and has much higher salinity, and the rainfall here has decreased. So this has to be the rainy season or the boreal summer season, and this has to be the boreal winter season. So you can also see the ITCZ being stronger here compared to here in the boreal summer, with the ITCZ coming north with the sun, and there are differences here as well. So the salinity difference here in the Pacific versus the Atlantic also adds to the differences in the ocean response to buoyancy. So when you have such high salinities and such warm temperatures, you have two things happening. The salinities themselves, of course, are related to the fact that a warm ocean is driving evaporation because the cold atmosphere is picking up all the moisture from the ocean. Its moisture holding capacity goes up. So we have seen that here as tremendous heat losses going all the way into the North Atlantic as compared to the heat that is somewhat into the ocean here in the North Pacific. So this creates heavy water called the North Atlantic deep water, both in the Labrador Sea and the Greenland, Iceland, Norwegian Sea. And there are other regions here in the Southern Ocean like the Ross Sea and Weddell Sea, where a bunch of other processes like sea ice formation, brine rejection or salt left behind when the sea ice forms, and just cooling because of the winds. You can see the salinities here are somewhat fresher, but you can see the temperatures are much colder. So the combination of temperature and salinity, of course, give us increased buoyancy flux or cooling and loss of heat, and gain of salinity and heavy density forming at the surface. So we end up with what are called deep waters, which actually occupy deeper part of the ocean, but they are formed near the surface. Okay, so we will just quickly add the conveyor belt here and come back to it. So the global conveyor belt is a system of ocean currents that transport water around the world, while wind primarily propels surface currents. Deep currents are driven by differences in water densities in a process called thermohaline circulation. Density depends on both the temperature and salinity of the water. Along this conveyor belt, heat and nutrients are moved around the world in a leisurely 1,000-year cycle. As it transports heat, the global conveyor belt keeps the Earth's climate stable by taking down heat and CO2, oxygen, nutrients, and so on as well. However, scientists have recently noticed a slowdown in ocean circulation. We'll come back to that in the next chapter mostly. With climate change and rising temperatures, the process may slow down even more and bring more extreme temperatures to different regions around the world. So the fact that this is a 1,000 years cycle means it has played a big role in long-term climate variability going back in time. We look at what is called paleoclimate or past climates, and pretty much no paleoclimate discussion is possible without bringing up the thermohaline circulation and the role of the ocean circulation in that sense in the long-term climate change. So come back and look at the processes in the next podcast, but there are key regions, the one we mentioned already here in the North Atlantic, which includes Labrador Sea and Greenland, Iceland, Norwegian seas, cross-Atlantic transport here, deep water formation and so on in the Southern Ocean, and the tropical pathway in the near surface where the cold waters that are formed and transported southward from the Atlantic into the Southern Ocean looped around here and inundating the Indian and Pacific Oceans, and on 1,000-year timescales getting converted back to surface waters by various mixing processes and coming back to the region where the sinking happens. Okay, so this is the thermohaline circulation, which obviously plays a critical part and is related to wind forcing and is part of the heat transport that is required to account for the fact that energy surplus region in the low latitudes don't keep getting warmer, and the energy deficit regions at polar latitudes don't keep getting colder. So energy transport is being done by the ocean and the atmosphere, and thermohaline circulation is a big part of the ocean heat transport. Okay, so let's leave this introduction here and come back and add some more details of how the buoyancy forcing drives ocean circulation, called the thermohaline circulation, which again is not really independent of the wind-driven circulation, but it's convenient nonetheless to talk about it somewhat independently of the wind-driven circulation. Okay, we'll continue this in the next podcast.